So it's my great pleasure to introduce Leslie Kaelbling. So Leslie got a PhD from Stanford University, advised by Niels Nielsen, and yeah, I think it's quite a pedigree, I would say, to have in the the signature in the thesis John McCarthy and Richard Sutton at the same time. So great, really great stuff. And so she joined SRI briefly, and then Brown University, and stayed there until the end of the 90s. And then in 2000, around 2000, Leslie joined MIT CSAIL, where she is currently a professor. And around the same time, something interesting happened in the machine learning community, because the entire board of MLJ resigned in opposition to the open access policy of Kluwer at the time, and Leslie founded the Journal of Machine Learning Research, which she has been the editor-in-chief for many, many years, and it's one of the top journals in our field. So in terms of contributions, she did measure stuff in robotics, in particular, in partially observable Markov decision processes, but Leslie also has some contributions in more core machine learning, like transfer learning and optimization. So I think today she will talk about robotics, really. And so please, Leslie, thank you very much for accepting our invitation. And yeah, the scene is yours.
All right. Thank you very much for the introduction. And I'm excited to be part of your kickoff of your project. And I was just looking at the website briefly this morning to remind myself what ELLIS was about. And I read what the acronym actually stands for. And I guess I wanted to point out that, like, my research group has been called Learning and Intelligent Systems since 1999. So, I was there before it was cool. Okay. So what I want to do is I want to make intelligent robots. And it's not because I really want to make robots to do any particular thing, but because this is my avenue for trying to understand really what underlies general purpose intelligence. And I feel like if I can make a generally intelligent robot, then I will have really kind of understood something about intelligence fundamentally. So an example problem I like to think of that's, not as ambitious as all of AI is making tea in any kitchen. So in fact, I asked my students to do this in a research seminar a year or so ago, which is to go to somebody else's house and make tea without answering any questions. So almost any house in the whole world, they make some kind of beverage involving hot water and leaves. And if you went into somebody's house, you'd probably kind of mess it up, but you would be able to figure out maybe where they keep the stuff and how they make their water hot and so on. And so the question is, what would it take to make a robot that could do something like that? So you want something that's very general purpose across domains that can do a variety of different problems. And so the question is, how do we think about constructing such a system, right? So I want to kind of frame the question in the following way. I think of my problem as let's say, a robot engineer, as a robot software engineer. So I'm not going to talk about hardware. I'm going to imagine that the hardware is fixed. And I'm going to imagine that my job as a robot software engineer is to be the robot factory. And I'm going to make these robots that have some policy, some software in them. General purpose policy takes a history of observations and actions, generates the next action. And the question is, what policy, what software should I put in the head of my robots? And I want to think about this a little bit formally in terms of a specification of the problem the robot's going to have to solve. So I imagine that you're going to come to my factory and you're going to order some robots and you're going to tell me, look, here's a distribution over possible problems that these robots are going to have to solve. So it might be that they're factory robots that just have to weld one spot on one car, in which case the distribution has almost no variability. And then the right program to put in the robot's head is a very simple, very narrow just program. On the other hand, you might tell me the distribution is all the houses in the world, and the job of the robot is to make tea. And then I have to put a different program in the head of the robot, right? So the question is, given a distribution over problems that this robot might have to solve, what program should I put in the robot's head? And one reason why I like to think at this level of abstraction for a little while is that it keeps us from needing to have religious arguments, right? So you might want to argue about whether the robot needs to do learning, or whether it has to have graphical models, or should it do inference, or is it all neural networks, or all these questions that we are like all arguing about at the moment. But really, if you frame the question this way, and there's a distribution over problems the robot's supposed to solve, then there really is an optimal policy. Maybe there's a whole class of optimal policies, but it will learn if it needs to learn, and it will not learn if it doesn't. And we don't have to argue about whether it needs to be a learning program or not, because there really is just a program that satisfies the spec. So that's good in a way. Okay, so this makes me temporarily happy. But the problem now is that although maybe I could make the problem well-formed, if in fact you could give me the specification, which is also hard. So I could make the problem well-formed, but it is really not easy, right? So if you give me a spec in terms of a distribution of problems the robot's supposed to solve, maybe there is an optimal strategy, an optimal program to put in the robot's head, but it's very hard to find. So this is a hard job for the engineers. But this is what now I'm thinking about as my problem. So the question is, how should I build in a program into a robot so that it can go out in the world and solve a wide variety of problems? So one way to think about this is to think about the space of distributions over domains. So what's the kind of space of problems that a robot might have to solve? So one dimension of complexity is sort of like the complexity of the problem overall, right? So if the robot just has to vacuum one house, well, then maybe that's a very simple program. If the robot has to be able to go to any house and do any household task, well, that's a very complicated program. So there's this kind of just dimension of complexity. And there's another dimension, which is basically, what do we know in the factory? So what do we know about what this robot is going to have to do? So very classical engineering kind of addresses this problem down in the left-hand corner, where we totally know what to do. It's a very specific thing. We write a program to do it. Everything is good. Over here toward the right is maybe where classical non-learning related AI has tended to be, right? We want a program with a very general capacity to do a very broad range of things. But we know in some sense in advance what the space of things is that the robot will have to do. Over here, maybe this is the realm of, say, reinforcement learning, right? There's a specific task that this robot is going to have to do, but it has to learn online what to do because the engineers don't know in advance what it will be. And this is like, well, I don't know where we hope to be, like over here in the upper right-hand corner. So how can we make policy? So imagine that we're given a distribution over domains. How can we make a good policy? And the way I want to think about that is the way that most machine learning people, I guess, think about solving problems, right? Which is that we have to pick some model class. And we have to think about how we're going to acquire these models. And we want to minimize, the way I think about it, the work that has to be done in the factory. And the kind of work that has to be done in the factory might be specifying models, building simulators, doing reward shaping, gathering data, and so on. And there's work also involving offline optimization, learning, parameter tuning, and so on. And what we want to do is somehow pick a model class, right? So a design for our robot software where human engineers have insight, because the fact is that human engineers are going to have to make it, where the optimization problems are not too hard, where learning will generalize well, and so on. So let's think about ways that we could represent a policy. And I have a kind of a detailed story. I'm just going to fly through it because I have a whole bunch of things that I want to talk to you about. Okay, so, but a policy, right? So in classical kind of MDPs or reinforcement learning or something, we think of a policy as something that just takes observations from the world and generates actions. So you could just try to specify the policy directly. It can be hard to search for policies. And so often we try to use dynamic programming where we learn something like a long-term value function and use that as an indirect implementation of a policy. This is great when dynamic programming works for you, which is generally when you need to solve the problems over the whole state space. But I would argue that as problems get more and more difficult, more and more, the policies become more and more complicated, the idea that you should be able to solve all the subproblems in advance is slightly crazy, right? Remember when you used to fly places and travel? Think of all the things that could happen to you when you're traveling, right? The roof could cave in the airport, or all kinds of crazy things could happen, and you would not have probably inferred in advance what to do in all of those cases, which is kind of what learning a Q function implies. So another strategy is to say, well, okay, I won't infer what to do in advance. Instead, I'll use some models, right? Some transition models, some utility or reward models, and so on. Maybe some bits and pieces of value function like AlphaGo does. And I'll make a planner which can infer what to do. And maybe that trades some computation time online for some work offline. Doing this at the very most raw level of actions and observations is usually pretty intractable, especially if you have a long horizon. So then maybe we need to build in some abstraction, maybe we need to build in some perception and so on. So we can build ourselves up to a fairly kind of modern technical architecture for a robot, right? Where we integrate observations over time to get some estimate of the state or a belief about the state, where we use inference methods to decide what action to take at some level of abstraction, and where maybe we use some lower level controllers to actually implement that action in the real world. Okay, so this is a strategy. We can add some hierarchy that makes it even cooler and so on. So classical engineering, right? This is the Atlas doing what it does. It works great for problems it works great on. Let me just make a little digression here for a minute, because this is a point that I want to make about learning, and in particular about reinforcement learning. So there's a lot of work, right? A ton of work on reinforcement learning at this moment. But what's interesting is that I would like to argue that almost all of it is actually focused on this lower left-hand corner. That is a case where what the robot needs to do is not too complicated in a sense, right? So manipulating this Rubik's Cube in the hand is complicated in one sense, but it's not super high variance in the way that like traveling the world is, or even doing any household job. And the engineers knew exactly what this robot would need to do. But what's interesting is that they still didn't know how to write down the policy. So I want to talk for a minute about reinforcement learning as a technique to use in the factory. So imagine a situation where we know exactly what job the robot is supposed to do and in what domain, and we know it so well that we can build a simulator. But we might be in a situation where we know how to build the simulator, but we're still not sure what the optimal controller is. So what we can do is we can run reinforcement learning methods against that simulator to, in some sense, compile into a policy or a value function, which we can then put in the robot's head, and then it can execute in the world. So I like, this is an important and a useful technique. It's interesting though, because it's not the same as the kind of original conception of reinforcement learning, which I'll come back to in a little bit. And I think the way that we want to think about this problem of RL in the factory is, in some sense, as a compiler, right? It's a situation where reward doesn't matter during learning at all. Exploitation doesn't even really matter. There's no sense of exploiting. The robot isn't actually vacuuming the simulator. It doesn't have to do a good job of vacuuming while it's learning. It's just learning how to vacuum. It's just, right? And so the number of interactions with the simulator doesn't really matter. And what I would argue is that in this particular situation, what matters is, as a function of how much computation you use over here in this compilation process, how good is the policy that results? So this is not usually the learning curve that people make in this circumstance, but I think it's really the right one, right? So reinforcement learning as a compilation technique. Okay, so this is one way to solve the problem of getting particular policies that do a job. There are now, people have been looking at problems where the complexity of the policy is bigger, but we still know the domain pretty well. In chess, we know the domain. I'm going to talk a little bit here about work I did a while ago called Hierarchical Planning in the Now, which attempts to move out on the complexity spectrum of building robots, but doesn't yet move up on the learning part of these axes. For a minute, I want to talk about the different settings between the kind of compilation view of reinforcement learning and this kind of somewhat different, somewhat maybe more traditionalist view where you say, oh, we're going to do perception and then use a planner and so on. So what do we have to do to make this work? Well, for reinforcement learning in the factory, we have to put in a reward signal. For this kind of class of this architecture over here, we have to put in a goal. It turns out that putting in a reward signal can be pretty tricky. So there's this very interesting suite of example problems for reinforcement learning. And if you dig into it, which we did, we looked at the reward function for one of the tasks. This is the reward function for the pick and place task. Right, so that's pretty complicated reward function. I went digging in there because I wanted to implement it in something I was doing, but this was just like, oh my goodness. So I decompiled it a little bit, and basically it's a little state machine that tells the robot approximately what to do. But to get reinforcement learning, plain old reinforcement learning to work very well, the reward function has to be really local and really dense. On the other hand, for our planning-based approach to these problems, all we have to do is give a goal, like the goal is that some object be at some location, and the planner can figure out what to do. So this is this planning formulation of behaving it's in some sense, I think it makes things easier for the human and harder for the computer. So if we go back to this kind of trade-off here, we say, well, in both cases, we have to give a description of how the domain works. In the RL case, the domain description will be used to make a simulator. In the kind of architecture on the right, the domain description gets used for the planner, but they're both useful things. Okay, one problem though, with this kind of higher level planning and estimation based view of building an intelligent robot is that we have to build these planning models at a little bit higher level of abstraction than the basic level of sensing and acting in the machine. So how can we think about what models to use, right? If we use the raw simulator, if we tried to plan using a raw level of the simulator, the time constants would be very small. The number of steps we'd have to take would be huge. It would be very difficult to do the planning. And so we need to build an abstract model, or maybe a whole hierarchy, a whole stack of abstract models so that we can reason efficiently. And so what makes a good abstraction? Well, it shouldn't make the computational, it should make the computational problem much easier, should not make the solutions be too much worse, not be too hard to implement, and so on. So for planning in robotics, we use an abstraction called multimodal motion planning, which I think I am not going to go into, although if anybody wants to talk to me about robot planning, I would be happy to. But it's a beautiful story about the kind of underlying topology of spaces that robots live in when they move in a combination of continuous space and discrete space, which includes the changes that happen when you, for instance, pick up an object or put it down. Okay, so by formulating a planning problem in the terms of multimodal motion planning, rather than doing any machine learning and just knowing the sort of like the ground truth perception of where the objects are, we were able to use our planner to solve this whole suite of robot control problems. Okay, so these aren't very hard planning problems, and this is just an illustration of that generality can be obtained without necessarily doing learning. Okay, so now I'm going to talk about how we take that planning and extend it to a kind of a bigger space, right? So hierarchy is a really important idea. Everybody believes it's important. People implement it in different ways. We use hierarchical planning in our setup to do kind of aggressive and optimistic execution and replanning. So we take a high-level goal and decompose it into sub-problems using old tricks from like Earl Sasterdotty and Nils Nilsson way back in the day. So we make a plan at a high level of abstraction. We take the first sub-goal and make a plan for it in a little bit more detail. Take the first sub-goal there and make a plan in more detail. And then we begin executing the primitive actions. And as long as they're doing what we expect, we keep executing. But if we try to execute this action and find that it doesn't have the result we were hoping for, then we have a kind of an architecture for re-examining and reconsidering the current set of intentions. And what would happen, for instance, if executing this action P1 didn't have the intended effect, if we couldn't continue executing this plan, we would pop that plan off the stack, make a new plan for this sub-goal, and continue. So we get a flexible execution architecture this way. All right, now what I'm going to do is show you a movie of a robot that does a bunch of things using that basic architecture, the planning style and that architecture. And what's interesting about this movie in a way is that any individual thing this robot does, a couple of undergraduates in a week or two could do much better than this robot, but the same basic code can do a wide variety of things. And for me, at least, that seems to be one of the hallmarks of intelligence, is a kind of flexibility and broad applicability. So here's a simple situation where the robot was supposed to put the blue box down where the soup can is. It sees that the soup can is in the way, and it's going to move it out of the way. So there it goes, moves the soup can, gets the blue box and puts it where it needs to go. Here's another example where now the green box is supposed to end up on the corner of the table. The green box is too big to pick up, so the robot figures out it can't pick it up, and so it needs to push it. There's something in the way. So in order to push that, it needs to get the thing that's in the way out of the way. Note that we never programmed it to do any of these things in sequence. It's just doing pretty general purpose planning and problem solving. It knows that pushing is unreliable, and it reasons that it needs to observe the object and localize it. Here we've asked the robot to go out of the lab. These chairs are in the way, so it decides to move them out of the way. Well, it moves the first one out of the way. The second one, it just brings along with it because we just told it to go out of the lab. We didn't tell it anything about the chairs. Here's one more example where we asked it to put a full oil bottle on the other table. It's gathering information about whether the oil bottle is full, so it picks it up to see what happens. Okay, so what's interesting about this from the learning perspective is that there was no machine learning involved in it at all. We just implemented it, and I think it gives us a reasonably robust way to make the robot do some things. So that's kind of gratifying in a way, but it required a fair amount of hand building, and the perception was not so reliable and so on. And so now our big emphasis is trying to figure out how to embrace some structural biases that we've learned that have been very useful in building the system, but to add machine learning so that we can acquire new models and operate in new domains more effectively. So we could say, oh, we need to do learning. Well, we'll just do learning in your house. But nobody really wants a robot to be doing its basic learning about physics in their kitchen. So we're going to kind of rule out basic reinforcement learning as a method for learning in your house. And think about how we can do learning in the wild, right? So maybe we're not going to do reinforcement learning in the wild, but what we would really like to do is take the best of learning in the wild and the best of kind of structured planning and reasoning systems and see if we can put them together. So I'm going to just now breeze through a whole set of different pieces and parts of this architecture that we've been working on learning strategies for. So one thing is, in fact, if you read papers, people will say, oh, task and motion planning, yeah, that's really interesting, but it only works if you absolutely know all the objects you have to operate on in advance. So we've been working on addressing that in a project we like to call MOM, manipulation with zero models. So the question is, could the robot operate on a bunch of objects that it has no models for? So here we have this robot. It doesn't know anything about the objects it has to operate on, but using pretty good perception, it can segment the objects, estimate the shape, reason about where it can grasp them, reason about where it can put them down, and so on. So we're using pre-trained perception models that give us ideas about these things, how to grasp, how to segment, and so on. And those are used as input to the planner and a replanning loop similar to the one that I showed you, so that we can do manipulation in a pretty general way over really general objects. So here's some examples, right? So these are running on the real robot. So one thing to notice, this sort of stuff down here, I don't think it won't perturb the audience I'm talking to, but many people I talk to, they don't know what are those funny parentheses for, and that's kind of gobbledygook, but it's a nice logical expression of what the robot's supposed to do. So here we are in a situation where the robot has never seen these objects before. It knows a few type predicates, like it knows what a bowl is. It can kind of recognize a bowl. And so it's given this goal of putting all the objects in the bowl of the same color. Oh, why did it do this? I'm sorry, something is happening. Okay, here we go. And so here it goes. So it's putting the objects in the bowls, taking each one. It doesn't pick things up completely reliably, but it's persistent. So if it loses something, it takes a look and puts it somewhere else and so on. So it's solving this problem. And now here, I don't know, it was supposed to put the objects on the opposite color mat. Again, it's not completely reliable, but it's you have a sense that there's something useful going on there. Here, the cup was missing. It couldn't see the cup. So when it moved the box out of the way, it realized that it had to pick the box up and put it somewhere else. So this runs now. We have better robot experiments and better stuff in simulation and so on. So this means that we don't actually have to have strong models in advance. We can actually work with objects that are new to us. Another thing that we've been thinking about is adding a new ability to a robot that's already somewhat competent, right? So when you teach someone a new skill, you don't teach them from scratch. If you're learning to play an instrument, you don't have to learn how to pick it up. If you're learning how to solder, you don't have to learn how to open the package with the solder in it, right? So the learning that happens in humans and that we would hope to happen in robots is incremental and compositional. You start with some set of abilities and you add something new. This is not reinforcement learning for a totally new job, because I don't have to relearn my kinematics. And it's not even transfer learning. It's more like an underlying compositional structure that seems important to us. So we've been thinking about, well, how can we take a robot that's already reasonably competent, let's say at picking things up and putting them down, and teach it a new skill? So right now, if you look at most of the work on robot learning, it's focused on individual narrow skills, like throwing something or pushing it or opening a door or juggling, right? So these are localized things. It could be very useful to learn them. But what we want to focus on is how we could take one of those learned skills and package it up so that we could add it to our repertoire, so that we can use this skill to set up other ones and use other skills to set up this one, because that's what we need for real productive behavior. So we're going to focus on adding a new skill to an existing set of skills using a general purpose planner. So here's an example of a skill. Imagine that I've tuned up a controller for pouring stuff. And now I'm trying to add that pouring ability to my general kind of ability to do stuff in the world, which means I need to know, what is pouring good for? What does it achieve? And what are the circumstances that I have to set up so that if I call my little pouring policy, something good will happen, right? So I might be able to describe that using something like a strips operator description, right? I have some skill, which is pouring. Maybe it has a parameter, which is the gain of the pouring controller. I have some preconditions. And in this particular example, I'm talking about the preconditions. The form of the preconditions is known. Although we're working on something right now that will back off of this. But imagine that we say, well, okay, if the source has to contain some liquid, and then there are these parameters in boldface, which are continuous values. Like I'm holding the source container with some grasp, and it has some shape, and the destination that I'm pouring into has some shape, and there's some relative pose between these things. And what I'm going to be interested in learning is this constraint. you can think of it as a relation on this whole set of continuous parameter values, on the gain of the controller, on how I'm holding the object, on the relative poses, on the shapes, and so on. And I'd like to learn a condition, the condition under which, a condition on all these variables such that if I pour in these circumstances, it will have the desired effect. So I can do this by generating a bunch of pouring actions in a bunch of different circumstances, and then framing a regression problem. So we say, I want to learn a mapping between assignments of values to this whole parameter vector, theta. So I want to learn a mapping from thetas to some score. I want to know how much of the stuff gets in the destination vessel if I pour in these circumstances. So we use GP regression because it helps us know what parts of the space we're sure about and what parts we're not sure about. And it helps us do kind of very well controlled and efficient information gathering. I'm not going to go through this in detail either, but I would be happy to answer technical questions later. It works pretty well. One of the things that's important, there's two things that are important about this. One is that the Gaussian process lets us do sampling for diversity. So after we've learned how to pour, we might learn that in fact, I can pour from one side and I can also pour, in the fancy backhanded wine waiter pouring methodology. And that could be useful because it might be that in some circumstance, I can't use the pouring direction that I would prefer because there's something in the way, or maybe I hurt my right hand, so I would like to use my other hand or do it in a different way. So we're trying to kind of learn the whole locus of successful instances of operating this policy so that given the larger constraints, we can still solve problems that we have. The other reason for that GP is because training is expensive. So we didn't study this using liquid because that would have been really hopeless, but we did pick up a lot of beans off the lab floor in order to learn what were good ways of scooping and pouring and so on. But as a result of this, we can take these learned operator descriptions and put them in with our other operator descriptions and solve a variety of problems. So in this movie now, the robot, in this case, the robot does know about these particular objects. So it knows the shapes of the objects, but it's given pretty general purpose goals. And the objects can be anywhere on the table, different numbers and so on. So like in this case, it's supposed to serve something by putting it in the bowl on the tray. There it moved the green box out of the way so that it could pick up the blue cup. There's nothing imperative in the stuff we write, right? This is all just planning and deduction about what it's supposed to do. Here it's, again, serving some stuff in the white bowl on top of the block. The next scene will show us something kind of nice. That red bowl is too far over on the side of the table to pour into. And so it reasons that it can push it with one hand so that it can pick up the cup and pour stuff into it with the other hand and so on. So this is pretty good. We're happy about this. It's pretty robust as these things go. And so this gives us a way now to integrate some learned behaviors into the robot's existing abilities. We have a kind of ongoing work on how to actually learn what the form and the shape of the preconditions is. I'm not going to talk about this in detail. Another kind of thing we can learn is search control of actually a couple of different kinds. So everyone now has, been impressed and amazed by AlphaZero and the various related pieces of work, which really focus on not learning about the domain, right? If you're learning to play chess, you know all the rules of chess in advance. It's just a problem of deduction to decide what first action to take. But what you learn when you learn to play chess is really, you learn how to think about it. You learn how to focus your attention while you're searching on the good parts of the search space. And so the question is, can we apply some of the same ideas to some robot problems? And so if we think about a robot that might have to move a lot of objects in a complicated world, we can solve those problems using some kind of forward search, for instance, in some cases. But what's interesting about this forward search is that there's typically a discrete and continuous set of parameters we have to pick. So we might pick which objects to operate on, and then we might pick which parameter values to use in those operations, like how to grasp something or where to put it. So we get this like really hopelessly enormous search space. There's the branching factor really is infinite, right? There's the discrete layer picks operations, the continuous layer picks real values. The other thing about this search that's really different from chess and most searches is that the expansion, one node expansion, is really very expensive because it involves calling some low-level planning methods. And so we really need to make the search efficient. And we really want to generalize aggressively. So here's an example where we have this robot and it's in this room and is solving a problem in this case, which is sometimes called NAMO, for navigation among movable obstacles. It's a little bit like NAMO, but its job in one case is to take the red box and put it in the other room. To do that, it has to move some things out of the way. Another version of the same problem is to take all the boxes and put them in the other room, which it can do, but it's also, that's tricky because it not only does it have to worry about what to move and how, but it has to put them in the other room, find a good packing. Now, if we're good at generalization and we've learned something about spatial relationships and how to move things, then what we might hope is that we could take what we learned in this domain of moving big objects and apply it over here to the problem of moving these small objects in a cupboard. So what we're going to do in this case, and I won't describe it in great detail, but the idea is that we're going to learn a Q function, right? So that's a kind of a cost to go function or a value function. But first, we're going to learn it at the top level in terms of the discrete actions, right? So if we can learn to guide our selection of which discrete operation to do, that will be a big help. And there's other stuff that helps with this, picking the continuous parameters. So we hope to reduce the effective branching factor and generalize. And the way we learn this Q function, the discrete Q function, is what's tricky about it is that the states here are not vector valued, right? One state might have 4 objects, another state might have 12. So we have to find a way of representing the states so that this Q function can generalize effectively. And we do that using graph neural networks. And we used some clever engineering design to pick the relations that are actually computed and stored on the arcs of the graph neural network. So for instance, we actually use a planner to compute whether this red object is in the way of reaching the green object. So that's a relation which we compute using the planner. And the graph neural network learns how important that is, right? So these occludes relations are things that we build in, but then we learn the value function in terms of these occluding relationships. Okay, and there's loss function stuff, and there's an existing heuristic which works really pretty well. I mean, an existing algorithm works pretty well. We tried a simple heuristic which works on some problems but not others. But we did find that learning this Q function works effectively in all the domains. And what's important is that we trained it only in this apartment domain, and it generalized to moving the objects around in the cupboards. Okay, I have one more idea, and then I'll be done, and I'll be happy to talk to everybody. So far we've been talking about solving big planning problems and maybe about finding abstractions. We talked about temporal abstractions a little bit in terms of hierarchy, but the idea that we need to generate abstractions, I think, is really important. And that instead of thinking about trying to make our planning algorithms scale up to solve bigger problems, what I want to do for a little bit now here at the end is think about how to scale our problem down into a small one that we can plan for efficiently. And you can imagine going through life with a small planner, but trying to figure out how to deploy it effectively. So we're going to think about some kinds of moderately complicated robot manipulation type problems. Again, they have complicated state spaces. And what we're hoping to do is learn how to take a problem, a state, and a goal, and build an abstraction that makes it easier to solve. So there's this notion of kind of angelic constraints. We're going to think about constraints that we can impose on ourselves, right? So constraints might be I'm not allowed to go in that room, or I'm not allowed to use these operators or something. And the question is, can we learn those, which constraints it's okay to apply to our planning problem, right? Because if you apply some constraints, it generally makes the space smaller. Okay, so the details, again, I'm not going to go into, but here's the situation where the robot, this is again a NAMO problem. The robot has to move objects out of the way in order to come over here and do something with this red object. But if it can restrict its attention to some of the rooms and hence some of the objects, then it can plan much more efficiently. Here, the robot has to pick some objects up and put them in these cupboards. And maybe it can ignore some objects, other objects in the world. Maybe it can ignore some aspects of the space. And so basically what we are able to do is learn to map the situation into some constraints that make the planning more efficient. So one way to think about what we're doing here is to say, well, if we were just planning, then we would have to spend a long time planning and we would get, let's say, the optimal solution. If we were just doing, say, reinforcement learning, we could try to do reinforcement learning and learn a policy, and it would run very quickly. But in fact, in this domain, nobody's policy learning method can learn to do something useful. And so what we're doing is we're learning to map the big problem into a smaller problem, and then we're calling the problem on the planner on the smaller problem. In so doing, we might be somewhat less efficient, but in aggregate, we end up with pretty good solutions pretty quickly. Yeah, you don't need to see this. Right, the robot can make a plan in a simple domain, but then actually go back and execute it in the original, more complicated domain. Another version of the same idea is trying to figure out which objects you can ignore. Right. So generally speaking, planning problems involve a lot of objects and many of them are extraneous. Can we learn to predict which ones are relevant? And most planners suffer a lot from increasing the universe. So another thing we've been doing lately is using graph neural networks again to try to take a representation of an initial state and a goal and score for each object how likely it is we think it's important to the problem. So we train this network, and then we do planning incrementally. We take the top scoring objects, like maybe we think, oh, maybe only B and D are important. So we try to make a plan using B and D. Either planning fails. If planning fails, we know we need to add some more objects. If planning succeeds, though, it might be an unsound plan. So we have to take the plan that we get, test it on the full domain, and see if it works. If it works, we're happy. If it doesn't work, again, we'll go back and add some more objects. So we iteratively start with very few objects and add objects in until we get a plan that's correct. And this runs much more efficiently than a whole bunch of other things. And it can operate in pretty complicated problems. Okay. So now I'm going to just do this trick. I, a long time ago, gave a talk at IJCAI, and then I relatively recently gave a talk at IJCAI, and I want to just highlight the differences between then and now. So way back in the day, I gave this talk and I said, well, there's been a lot of progress in algorithms for supervised and reinforcement learning. And now what can I say? Well, now I can say like really a huge amount of progress. Like I thought there was a lot of progress then. That was like the second time neural networks were cool. Now this is the third time neural networks are cool, and they're way cooler. Okay, so that's good. But I thought then that it didn't really give us solutions for building autonomous systems. And maybe now I would say, well, we're starting to get some autonomous systems. And so that's good, but we're certainly not getting generally intelligent ones, right? So there's still a big gap. And then I thought, and I still think, that human insight is needed to complement the strengths of these algorithms, right? So my original theme was doing for our robots what nature did for us. So the question is really, what do we need to build into the systems, the AI systems that we're designing, that will complement learning so that we get a system that's very effective? And so what I really think now is that, algorithmic and structural biases, the designs of convolutional networks and graph neural networks, various kinds of planning and search methods, various kinds of abstraction methods, and so on, these are the things that I think that we as engineers can design that will give a lot of leverage to the design problem and to the effectiveness of the systems when we deploy them out in the world. So this is work I've done with my colleague Tomás Lozano Perez and many students. And I'll let you watch the robot make mistakes just so that you know it's real. And I would be happy to answer questions about anything. Thanks.
Okay, great. We are really in time, so there is plenty of time for questions. And if anyone can also please sort of forward to me the questions from YouTube, because I cannot see them.
I see Christian has his hand up.
So Christian raised the hand, so please.
Yeah, so first of all, no questions on YouTube, or I'm using it wrongly, but anyhow, I'm sorry about that. I have a question. Is it wrong to say that what you did with this simplification, where you say, let's drop some objects, the simplest case, is that a bit like the self-supervised learning, and we may call it self-simplified learning? I'm just wondering whether there's some connection, because you then also said, okay, and if it fails, it tries to even simplify further, or then later on it challenges itself again by adding complexity. So wondering whether there is something.
No, so that's interesting. It is self-supervised in the following sense, right? It's when it tries to make a plan, whenever it makes a plan with a few objects. Well, it sets itself a problem. So here's a problem, and it says, all right, I'm going to try to solve it with these two objects. If the plan fails, or if the plan is unsound, that's a negative example, which says, well, that set did not suffice, right? And I need more. And then it will start adding more objects in until it gets a sound plan. So you're right that in that sense, it is self-supervised, which is important because obviously you don't want a human supervising it, but it gets supervised. It presumes, though, that it has a functional planner. Right. So this is all about simplifying, given that you already know how to plan in the domain and that you have the domain theory. But yeah, that's right.
And then I would love if before handing over to Stephen, who was also raising his hands. So I recall that you were always challenging us at MIT with this question of, you know, you have a bunch of nails, and now what does it mean to have enough nails? You know, and there's this horrible threshold of one nail left, but you don't keep maybe at home how many nails you have. Do you think we can make some progress there by, if I understand you correctly, you are saying, okay, let's talk about constraints, and maybe constraints, we can, some of them, encode or learn implicitly. And maybe that's also a way to deal with this situation where you put some hard constraint, there should be at least one, but then I still have some implicit functional representation of what is enough. Yeah, I don't know. Or do you think we can make progress there? Because that problem is still getting on my nerves. I mean,
yeah, I think we can make progress. I think there's a couple of things. So what's interesting about the imagine that I have a jar of nails, right? And I need to do a project. One thing is, obviously, you don't want to reify all the nails in the jar, right? That's like a nightmare. And you don't even want to score them like, oh, is nail 51 useful? No. Yeah. So that method I showed you doesn't exactly address that. I did have a student, Natalia, who you might remember, who worked on thinking about equivalence classes of objects. And I know that, and there's been much work in this general area in like the ICAPS world. So sometimes you can say, well, I have this equivalence class of nails, and really, I can treat them as being all the same until I operate on one of them, and then it becomes special, but different from the other ones, and so on. But it's an important question. Again, I think that we could add this into our framework, which is to say, when should I treat the jar as a jar of interchangeable things, and when do I need to name them individually? And hopefully, maybe you could learn that.
Yeah, and that's interesting because somehow, this exchangeable idea, I mean, in lifted inference, we have it, in the equivariant learning, you have it. So this seems to be a general notion popping up all the time, but no one is learning when to apply equivariance or exchangeability. And that seems to be pretty important in my opinion. Yeah,
Right.
okay, thanks.
Another related idea, just something we've been thinking about, is also kind of the generalized planning, or the idea that policies can be rich and exist at higher levels of abstraction. So for instance, you might also do something that involves a jar of nails, which is something like, well, there's a place that needs a nail and a jar, hammer in the nail, right? And then get it, so that a policy could iterate over objects and just name the objects in terms of their properties and assume that they exist, or ask the question of whether they exist. But I might be able to make a plan to hammer in 100 nails that doesn't involve reasoning about all 100 steps. And again, there are great ideas about that in the literature, and the challenge is to figure out how to take them and use them and integrate them into a kind of a coherent approach.
Yeah.
Okay, so Stephen?
Yeah, so you suggest we should program in what nature has not provided for us with the robots, but what do we do with hard to specify but useful, constraints for useful tasks? So imagine I ask my robot to just, let's quote, tidy up the kitchen, and I give it the simplicity reward function and some general actions and fluents it can use. I come back from the shops and I find it's placed everything into the dustbin and put the dustbin outside the house, and the rubbish collectors have taken it all away. Okay, so that's not what I intended. But almost any human apart from a 3-year-old child would surely do a better job. But we never really explain to any human what tidy up means.
No, that's a great question. And I've been thinking about a related version of that, right? So this is, generally the sort of value alignment problem, right? How do you make sure that your robot or your agent has the same values that you do, or maybe values we wish you had? But right, so if I sell you a household robot and you ask it to do something, you make me a sandwich doesn't mean at all costs also, right? Make me a sandwich means subject to some reasonable constraints and not setting the house on fire or spending my last dollar and so on. And so it feels like that maybe there's a notion of a kind of, I think of it as like a background utility function. Maybe we as a society could think of some big collection of social norms and safety constraints and something as a value function that gets programmed in the factory. And then when you ask the robot to make you a sandwich or to tidy up or to do whatever task, that's a kind of additive thing, or that it's executed subject to the background constraints. I don't know how to do this, and I agree it's a very important problem.
That sounds like an appeal for common sense, a common sense reasoning program, maybe even.
Well, it is, but calling it common sense doesn't help us. I mean, we still don't know how to do it.
Exactly.
Okay, there is a question from Michela. Michela, you want to read it aloud?
Yeah, so it's okay. I mean, so first of all, I mean, that's a great talk, Leslie, really fantastic. So I have a question about the learning on constraints that you use in your precondition. So basically you are giving kind of examples of solutions and non-solutions of this constraint. So first of all, I would like to know, I mean, if you really have to give many examples or just, I mean, kind of, some of them. And also if you are in the interaction with the user can be helpful, because there are some papers that are connected with constraint acquisition. I mean, I come from the constraint programming community, and they seem to be very similar. We provide examples of solutions and non-solutions, and then the system learns the constraint basically. So I wanted to have some more detail about that, but really, thank you very much. Great talk.
Sure, thank you. We try to use, I mean, as you saw with the beans, every single example is incredibly expensive. And so we use this Gaussian process, which basically estimates our certainty that any given point in the parameter space is satisfying or not satisfying of the constraint. And we explicitly construct experiments to do that should be maximally information gathering, about the boundaries of the constraint set. So it's interesting because it's a different information acquisition objective than people usually use. We're not trying to find the optimum. We're trying to find the boundaries of the constraint. And so, and it's also important that we'll never find it exactly, but by maintaining an explicit representation of our certainty, what it means is that during planning, we'll try to pick parameter values that we're sure satisfy the constraint. But if we have to, we'll move toward the boundary. But again, we're aware during planning, we're aware of the fact that we have uncertainty about exactly where the boundaries of the constraint are. And we try to stay in if we can and not go too far out.
But is it a continuous process or just, I mean, you do it offline kind of, you know?
Right now it's offline, which is not what I would wish for, but that's how it is.
Okay, thank you very much.
Sure.
Okay, well, we wait for more questions. I have one question myself. Actually, so I saw a couple of connections to Metalearning in what you described. One is like, you know, this distribution over different environments or tasks, whatever. Yeah. And the other one is that you're using this GP, which is kind of, you know, like an acquisition function like you do in hyperparameter optimization, which is to me very closely related to Metalearning. So I wonder if you sort of see this connection as well, or if this would be just a bad idea to try to go in that direction.
No, I mean, in fact, right. So I think, you know, in between, there's the case where the engineers know everything about the domain and the case where they don't know anything. In between, I think, is in some ways where Metalearning goes, right? So you might say, well, okay, in the factory, right? Well, not in your house, but in the factory, we'll do Metalearning to try to learn how to operate in anybody's kitchen or how to learn quickly, right? So what would you do? You'd say, well, in the factory, we do Metalearning on a bazillion kitchens. So we make this robot which is ready to go into your kitchen and adapt in just a few examples. So yeah, I think Metalearning, Metalearning is the other strategy to use. When the engineers don't know what to build in, then Metalearning is the only alternative, I would say.
Okay, thank you. So wonder if there are more questions coming. So, yeah, if not, I mean, I would like to thank again very much, Leslie, for this brilliant talk, and really thank you very much. And